FM, because on FM user give each music their own tags. So we selected the most popular tracks with the most popular tags, and we checked some music items. We are more or less sure that the ground truth will be reliable, at least 95%. And then here are some examples of the formed social queries. We found 236K around social queries, and 200K of them were used for training. We also used a subset of the 200K to show that the generalization performance will increase while the number of training samples increases. Here are some examples of the social queries. For example, if we only sample genre dimension, we may have some social queries with, for example, find me the music with style classical, or with style disco, or hip hop, and so on. And if we sample more than one music dimensions, mood and instrument, we may have some queries like happy violin or something like that. And maximum, because we only constructed 4 dimensions, so maximum we can sample 4 dimensions, having some queries like find me the music with style, happy classical violin, maybe with female vocal, something like that. In this system, we use all these kinds of queries to train it and to evaluate it. Previously you have seen the search cycle involves multiple search engines as the underlying modality. So to implement the system, we also need to provide text-based retrieval and audio content-based retrieval. In this paper, we only provided 2 modalities, but within the audio content modality, we have different dimensions, music dimensions. And here are the implementation details. Search normalization, fusion, and relevance judgment is something relevant to the returned result list. For example, in the ith ranked list, we need to normalize the score of each returned result so that we can fuse them later on. Once after normalization, we fuse them by using the linear fusion case. This case, previously we know the query-dependent fusion module will give us a series of weights. So by getting the normalization score here, we can combine the weights with the score and come up with the final score for each document. Once we have the score for each document, we can rank them. That's the final list with fused ranking scores. Once we have such a list, we need to judge their relevance so that we can evaluate different search process, the quality of the different search processes. The relevance of a returned music document is ranked this way. If the query requires n music styles, and m of them matched with the ground truth, which is the query, with the requested styles. So we say this return item has a relevance score like this, m over n. So which means if the query requires 4 styles and the return item matches with that 4 styles, the relevance score is perfect, is 1. Yeah, otherwise, it's some partial score. The metric we use to evaluate the overall performance of the system is the average precision and mean average precision, and also the average running time. We re-implemented the previous query-dependent fusion approaches, which are the class-based query-dependent fusion, single class and mixture of classes, and also the KN approach. We also, in the regression case, to compare our learning algorithm with other popular algorithms, we employed libSVM to implement the regression model. Here are some results. In terms of effectiveness, we focus on this figure A first. Figure A shows the MAP mean average precision for different methods when they are trained using different number of training samples. So if we look at this direction, we can say that the overall trend is that the more training sample we have, the better performance the system will perform. So it means because the system relies on the training query knowledge scope to generalize its performance. So this really means the more training sample we give it, the larger scope it will train itself, so that against future user queries, its performance will be better. This validates the usefulness of our social query space and the automatic approach of forming a large number of queries. Previously, the previous approaches they only have 100 around menu design queries. So if that's the case, their performance will somehow align on this vertical line. So compared with our approach, the performance has been improved. And if you look at this direction, for any given number of training samples, different approaches performs differently, of course. But when the number of training samples is large enough, the regression approach will exceed. But during this portion, when the number of training samples is not that enough, some other approaches, like for this one, is the mixture class-based query-dependent fusion performs the best. And okay, so that's the effectiveness. In terms of training time and prediction time, that's about the efficiency of the system. We will see that our proposed learning algorithm can train the system very fast, and also in the prediction phase, it's very fast. Here are some details. I think we can escape. It tells us the performance along different music dimensions. The overall observation is the same as the previous picture, which is two aspects. The more training sample we have, the better performance system will give us, no matter of the method. And the second observation is that the regression approach gives better performance when enough number of training samples are given. And the last slide is about the robustness. Okay, so if I ask you a question, from each figure here represents the parameter configuration against their performance. So if you look at these 6 pictures of 6 methods, so which method you will say has the best robustness? Robustness here, we mean that in one way, we can mean that it's easy to tune the system. So because in system development, you have different parameters to configure. So if the system is easier to tune, so the performance is, how to say that, can be predicted much more easily.
The last one.
Oh, the last one. Okay.